Just 1 minute, please have a seat. It's time to restart. We have other 3 presentations before lunch, so we have to restart. Is everything okay from internet? Connection here is not working, but I hope that people from internet are following also the conference. So we are nearly ready to restart also for people connected on internet. Just 1 minute. Well, the next speaker is Giovanni Masotti from Elen. Please, Giovanni, come here. We always remember in Bologna that we started working with laser, with your laser, a 3 kilowatt CO2 laser, maybe 20 years ago. So probably if we are here today, it's also thanks to your laser. Maybe it's your fault that we are here. No, it's a joke. So I think all the people are coming. So next presentation is hairpin laser stripping. The speaker is Giovanni Masotti from Elen. Please, Giovanni, 15 minutes, so then we may have other 5 minutes for questions.
Sure, I will stay in time. Is there any way to have this working?
Yeah, it should work. Yeah, the desktop is not working here. They're still having a coffee.
Yes, as you said, it's a while that we know each other and we have started working together, so it's, I feel at home somehow.
Yeah, it's true. Well, seems it's working. Okay, no, Giovanni, the stage is yours.
So thank you, Alessandro, for inviting us, and good morning, everyone. So we'll be focusing on advanced copper hairpin laser stripping. Elen, I mean, we, between all the giant competitors that we have been listening before, Elen is a smaller one, but we are Italian, so this is, I think it's something to be proud of. This is somehow where we are around the world. I don't want to spend too much time, as I know that we are a bit in a hurry. So we are small, but we are growing. So these are our figures, and so we hope that we will keep this trend in the years coming. Okay, so I wanted to stress one point. You know, Elen is, we just deal with the laser both in the industrial and medical division. We have, as I was listening before from Stefano, that they don't know how many applications they have in the e-mobility sector. Somehow we have thousands of applications in the e-vehicles, especially in the most important component of it, that is the user. Because our medical division is able to provide many laser applications to the user. But joking apart, let's focus on hairpin laser stripping. You know that hairpins that have not been so much stressed in the morning are one of the most common winding components for high power and high efficiency electric motors for powertrains application. Usually we are dealing with high conductivity metal, so copper, and you know that the material that is used is isolated with multiple coatings of polymeric layers. The welding process requires clean and decoated conductors for the best results. So we have been listening to welding applications, and we have very smart solution for improving the quality of welding, but the first thing to take care of is to prepare the hairpin for welding. Otherwise, all the tricks are much less effective. So what our, let's say, welder friends wants to get is to have a real clean hairpin without or with the smallest amount of residual on the surface. So you know that to prepare hairpins we have two ways. One is mechanical, so with tools, or using lasers. Users to say that the traditional approach is much less flexible and has also some disadvantages in terms of how the copper is treated. Said that to get the proper quality, the settings, especially if you change the dimension of hairpin, requires time and skillness. The laser is a fast, efficient, accurate, industrial proven process. Obviously, the laser doesn't have any contact tools, so the parameters can be safely stored in the recipes, so you can change production very easily, getting the machine set up in no time, practically. So this is the typical hairpin, and you know that the edges has to be fully clean in inline solution. Usually what happens is that you have the line that forms the hairpin, and then you need to prepare it up for the next steps, that is welding and mounting on the stators, and the edges have to be fully clean, as it happens here in this picture. We are still in love of CO2 laser, because we are seeing new application every day. So we started from CO2 application. I mean, CO2 wire stripping is let's say, an old application, and that was the starting point, especially for us, for cleaning up the hairpin. We ended up in finding that CO2 itself was not fully cleaning the copper, and so we coupled CO2 with fiber lasers. How we do it is that we have the stripping station that is based on obviously laser sources and the galvo scanning system in order to speed up the cleaning process. Usually what it is that we have a galvo head that is controlled by fast, real-time, software-driven embedded solution that can work on the fly. So it means that we don't need to have any stop-and-go process based on laser needs. So we can remove all the, let's say, the insulator around the conductor while it moves, and while let's say, the line is forming the hairpin. The quality of the cleaning, so meaning how much of the isolating coating of the copper is removed, at the very beginning looked to be an easy job, because the copper looked very clean after just a quick pass of CO2. But then we realized that the micron, let's say, thick residual that was on the copper was not really friendly with the further processes like the welding. What we base on our, let's say, feedback in the cleaning, the stripping, is the RFU meter, that is a relative fluorescence unit meter that consider how much of the fluorescent contamination has left on the surface. So Hélène has developed, I mean, we have started the beginning with little players, then now we are working, this is disclosable, with Atop, that is a IMA group company, with which we have developed an electro-optical platform that obviously is available for integrators. So it consists in laser sources, galvo scanners, hardware controllers, software development kit for PLC integration, and let's say it's the whole solution for stripping process. We are in love with CO2, but we have realized that it's a combination of the two lasers that gives the best results. So our platform includes both CO2 and fiber lasers. What we do is to have the CO2 doing the dirty job, so meaning that we use CO2 power in order to clean up the major part of the isolators. And we use lasers that ranges from 300 to 700 watts. And this is, I mean, obviously, the more power you use and the quickest is the process. The advantages of this solution is that the absorption of the radiation of CO2, so the 10.6 microns, is very selectively absorbed by the material. So as long as we talk about the, let's say, the plastic-based, polymers-based coatings, they are easily sublimated by CO2. They fully absorb CO2, and the CO2 stops when hits the copper. So there is no real interaction between copper and laser. So we don't heat up the copper, and we don't touch the surface. We don't engrave it. We don't scratch it at all. It's a fast and robust process because, I mean, given the fact that we have this selectivity in absorption, we don't really have to care about very, let's say, fine tuning in the because we have a nice threshold that works with us. Given the fact that CO2 leave this micron of material, the copper that is cleaned by CO2 is not doesn't oxides because we still have this tiny protection. Obviously, this can be also a disadvantage because we still have these little contaminants on the surface that we can test with a few instruments. So in order to provide a full clean surface, we have coupled CO2 with mid-power pulse fiber laser. So we don't need too much of power with the fiber laser, but we still need it in order to get rid of this very tiny insulant left. So advantages are that we can reach very low RFU values. So low RFU values means that no polymer is left on the surface, or almost none. And this allows, obviously, a good welding process afterwards. In this way, we don't have too much production of smoke and dust because, as I said before, the dirty job is all done by CO2 previous treatments. Users to say that we have disadvantages like the fact that in this case, we don't have the famous threshold I was saying before. So we have to fine-tune the process in order not to have the fiber, the powerful fiber laser, to be too much aggressive on the copper surface. And having a clean copper surface, it oxidizes much quickly. So this is the standard architecture. So we have the first station that is CO2-based station with the two Galvo scanner head that clean up, as said, the major part of the isolating on the copper. And then so this is the typical mirror beam path, based beam path. And then we have the same, let's say, architecture in terms of lightening the wire. But the two, obviously, scanners are, two in this case, are fitted by fiber lasers. We have been talking and thinking about the best geometry in terms of how many heads using in order to speed up the process and to, let's say, and to keep the cost of the plant reasonable. So we still think that two couples is the best optimization based on our experience. So we tend not to have, obviously, the two scanners that lights up each other. Is manageable, but in this way, it's a safer solution, as we have tested, especially in mass production. And I mean, the fiber laser on which we base the fiber station is IPG, because it's the best, let's say, let me say, compromise that we have found, both in terms of quality, price, and we have a long-term experience with this kind of laser, and so we know them very well, and we trust them. In terms of CO2, obviously, is fully made in-house, and we have rejuvenated, let's say, the CO2 laser concept, having our never-ending power solution that is based on lasers that have got a laser cartridge able to refill the laser. So we have this family of laser that goes from 300 watt up to 850 on the same size of laser. Then we have also higher power up to 1.5 kilowatt based on this self-refilling technology. We're talking about a pulse laser that can reach peaks up to 1800 watts in this family range. We have obviously the spatial filtering inside, so we have a very nice 0-0 mode M-square output. We have integrated 1000 Ethernet CIP connection, shutter with red diode laser in it, and this is very helpful, obviously, for the tuning of the process, for the alignment. Safety shutter, so we have a lot of, let's say, supports to make the laser very easy to integrate. So this, okay, it's not, I will skip the little movie about the self-refilling technology, but this is something that allows the laser not to need to have been refurbished or replaced in the time being, because virtually it's a never-ending laser in terms of the fact that everything that is, let's say, getting worn in the laser can be easy refilled by this gas cartridge that we provide. And this, especially in the automotive industry, where you know that downtime is not an option, this kind of laser allows, let's say, virtually endless and very stable process with a constant and consistent power. The other key components of the, let's say, of the station is the galvo head that in what we have, let's say, put together for this application is the 3-axis 35 millimeters optical aperture scanner galvo head with very low inertia beryllium or, let's say, special alloy mirrors driven by digital drivers, with the third axis that in real time adapts the focusing of the laser, and with the field of view that goes up to 500 by 500 that we have seen that in this field is what we need. And usually our heads are both able to manage CO2 and 1 micron fiber laser. The control unit, so we provide the whole system, so laser source, galvo head, and the control unit itself. It's a real-time one. Okay, a standard, industrial standard, so 19 inches, 2 units industrial rack with multi-range AC input, Ethernet connections, simple single cable that links the control with the head both for signal and power, software library available, and optocouple I/O to connect to the rest of the system and for the encoder input for the inline processes. So this is the quickest way to show you what we deal with.
Thank you, Giovanni. Very interesting. Thank you also for being perfectly on time, so we don't have to. We have time for a couple of questions, if any, from the audience. One question over there, please.
Hello, hi. Thank you for the very nice presentation. So I had one question related to the how you qualify the output of the laser stripping process. And I was wondering if you're looking into new solutions, for instance, in order to understand if this laser stripping process has been done well, as an alternative to the RFU measurements, which we know are complex to integrate in line in the production process. Thank you.
Thank you for your question. We, as you know, RFU is now the standard. Maybe that tomorrow our partner will be talking more in detail about this aspect. As far as we, let's say, as we know, there are other methods that we are still not able to disclose. Let's see if our partner tomorrow will do. But still, we are there. We are working on something more in line and more, let's say, reliable. Also because RFU measurement is very. I mean, I have our guys here that have a fight with it very hard because it's not a quick and especially reliable measurement. So you have to carry out several in order to make sure to have the right data. So it's not something really industrial grade, but it's still the standard. But there are other still in the oven, let's say, that we are cooking. So we will disclose. Okay, thank you.
And any other questions? Let me check if we have questions from people on the web. No. So no more questions. Giovanni, thank you again for being here, for your improvement. See you later. So it's time for the next speaker from Optoprim. Salvatore, please, Salvatore, come here. His speech is about tailored solution from a partner in LaserEMobility, results from wavelength and beam shaping blend. Please, Salvatore, stage is yours.
Thank you.
About 15 minutes, then
I'll try to do that.
Okay. Thank you.
Good morning, everybody, and thanks for you to hosting this meeting, which has been very interesting for us, to challenge us. So let me give a couple of minutes to introduce Optoprim, as maybe is not well known like the previous company who had the speech before. So Optoprim, this is the index of what I'm presenting. So an overview of Optoprim, some in-depth on what laser can do in e-mobility, and then a couple of applications examples. So who we are? Optoprim has been established in 1994 in France as a distributor for optical components, and then has enlarged in 1999 in Italy, and then 2004 in Germany. Nowadays, we are about 85 people, and 30 of which are in Italy. The main turning point, and this is what I would like to stress in this speech, is that in 2014 we established in Italy a laser application lab. So the target of this small section of Optoprim, which is actually growing, is to deal with application from customers and use the knowledge we have learned, we have gained during the past years as distributors. This is a quick overview of how the application lab is today. We are quickly going to move into another building where the application lab will be larger with dedicated cells to applications. And we are dealing with several kinds of lasers, so different wavelengths from CW to femtoseconds, and also with optics and measurement instruments which enables to check how the laser is performing, and also to check the results of the process we have performed. The type of applications, as we have different people, application engineer dealing in the lab, we try to focus on different applications with different selected people. And we go from cutting to micromachining to welding, brazing, any kind of application that can be done with lasers. And as said, we have the key components to properly deal with each of these applications. So why we are offering us as a partner to integrators in Italy and in Europe as well? So as said, due to our knowledge, being a distributor for several years, we are in touch with the key world player for the different parts you need for a laser system. We can select the technology depending on the need of your specific application, and we have also the experience to put together the different parts in order to get the best out of it. Also, we support our customers doing the first initial test, supplying the subsystem, installing and have it running, and also the after-sales support. So it has been already covered in a previous discussion, so I'll go very briefly through it. In e-mobility and building an electric vehicle, you have several items where the laser can be used to address specific needs, mainly batteries and packaging and pairing, and also the stator. And here you need laser for cutting, welding, marking. All of these can be addressed by our solutions in our lab. As said, for the use of these, or to the building of this new equipment, you need to use some specific materials, and some of them are more tricky to be used with laser. And I wanted to focus here on copper. It has already been said that copper at ambient temperature has a low absorption, and instead in the infrared wavelengths, but has an higher absorption in the blue. So depending on the specific need, you would either go for higher intensity infrared or instead move to the shorter wavelengths. And we can do both. So we have setups that can cover both demands, and in some cases, the first one is winning, the second has other advantages. So let's have a look into the first application, is regarding the manufacturing of the internal part of the battery, and where you have to deal with thin sheets of copper, aluminum, and also with a coating on top of that. And the need, as they come in rolls, is that you have to cut them and have good geometries without or with a very few burned part. So all this information tells us that the approach is to use a remote laser cutting. So what a remote laser cutting is based on a laser. In this application, we are going to use an infrared laser, a fiber laser with a single mode, so that we can have a very fine beam, and so have an higher intensity in order to properly treat copper, and also a scan head with an f-theta lens that can allow us to go very fast and cut over a large area these foils. The type of material usually, again, is, in this specific case, was copper. Usually is 20 micron thickness, and you have a coating on top, which brings the total thickness up to 150 microns. And here is the result. So as you can see, is a very fast and very nice cut. And we had afterwards an overview of the result on the cutted side, and we were able to achieve what the customer was asking for. So a depletion zone below 25 microns, so the area where the overlay part is still present, and a minimal bar of the cut. The advantages of this approach is that is more flexible than mechanical cutting, so you can change shapes, and is a modular design where you can add multiple lasers, multiple heads, and so have a higher throughput. Next, so we wanted to give an overview of what we are capable. So in this, in the first one was a cutting with an infrared. Next one will be instead welding with the blue. And where these we think has a benefit. So stator design requires the need to use copper and in different shapes. Stripes or hairpin, also different sections. So different approaches are required depending on the specific need. Infrared has already been seen, and we have the ability to use this as well with wobbling, but we wanted to show a different application where instead up to 8 millimeters square of section, you can benefit from what the technology has brought, so the blue laser. I said what the weld needs to provide is low spatter, low porosity, a good penetration depth, low cycle time. Also, I want to remark that the process must be robust against some mechanical disalignment. So during the positioning of the pins, there might be some misalignment which has not been wanted. So either you have a vision system which helps you in doing a good position, or we can have a more tolerant setup that can support you. So blue laser has already been discussed a bit, but I wanted to stress that blue laser is already in industry and manufacturing since several years. So it has been used and is a reliable source. It started with 500 watt in 2018 and has been growing in power and application spread. Nowadays, we are able to supply 800 watt when used through a scan head, or up to 1.8 kilowatt if you want to use a fixed head. And within the end of this year, this power will increase as well. The other advantage is the fact that is based on the direct emission of diodes, so there is no conversion efficiency and there is a very high wall plug efficiency. So I said the application is welding of hairpin. The setup will be a two-scan head, two-axis scan head in order to correctly position over the different pins available on the working area. And we are using a 1 kilowatt blue laser coupled to the scan head. This results in a large spot, which will give some benefit, and an optimal power absorption, as copper is very absorbing immediately at this wavelength. So here we show the result. The first video just shows with a visible laser the process at the normal speed. And then the second one should show the real process with the blue laser in slow motion. Which is most important is the last one, where you see in high-speed imaging the very calm process due to the high absorption of the copper already at room temperature. So there is, in the video, no sputter at all, and the melting pool is very calm and stable. We have gone through inspecting the sample, so again, due to the high absorption to the blue, we have a fast, reliable process with very good weld quality, and through the cross-section, you can see that the porosity is very minimal. The other advantage is that in this setup, you can have a spot onto the sample which is ranging between 500 up to 700 micron. So it can be more robust depending on the different sizes of the hairpins, or if there is any misalignment between them. So in this video, you can see that with the same setup, you can process easily different parts with different shapes, and also if parts are misaligned, because the larger spot bridges the difference, the gaps between the two. Also, you are capable to do other stuff where maybe you have a bundle of wires, and as the spot is large, as the absorption is high, you can easily melt them properly together. And in the video, you see that the process is very quick and calm, and on the other side, you can see the quality of the weld. So, as a conclusion, I just want to highlight that we have a comprehensive set of lasers and heads in order to process virtually any laser application. We have the experience and knowledge of our company, but also with the support of our partners worldwide. And our core business is the success of our industrial customers. So we want to be their R&D lab for lasers. We are not dealing with integration of production lines. We just want to add our knowledge to the knowledge of the customer. The turning point for our customer will be drastically reduced time to market, which is crucial in this specific opportunity. And we are able to supply a very reliable product. So this is the end of my presentation. I thank you for that, and I invite you to visit our tabletop on the other room, where we have also another system running, and we have some giveaways in order you to remember about Optoprima in the future days. Thank you.
Thank you, Salvatore, for your very interesting presentation, for being here, and also for support us as a research group. Most of the results that we have are thanks to the laser that you gave us. So thank you also for this.
It has been a pleasure.
And are there any questions for Salvatore Optoprim? Okay, just one.
Hi, Salvatore. Thank you for the presentation. When you cut the foils with the CW laser, the coated foils, how can you manage that drops of melted materials are not ending on the surface of the electrodes? That is something that happens quite easily with the CW laser. Did you check, and how you can be sure of that?
So I've not the complete reply to that, because I have to check how much material was dropping. The other thing is that we used the modulation in order to lower the heat transfer to the material. So it is not just a pure CW, it was also highly modulated.
Okay. Any other questions? Sorry, let me check if we have a question from... Yes, probably we have... Yes, we have a question from the web regarding the laser stripping of high pins. Is the... Probably, I don't know if this question is for you or for Giovanni. Is the insulation of all edges of the wire captured and fully removed with the dual, I can't read very well. Probably it's not for you, sorry, it's just arrived. And I have a question for you.
Please.
As you know, we are now testing the blue laser in our laboratory. Which is your impression about blue lasers on copper, obviously? What can you say us? Which is your feeling?
Thanks for asking that. So, as all the different lasers it is an additional tool that we have, and so as it is also young, we have not exploited at its best the opportunities, but for sure is, we think, the best choice when you have to weld thin foils, or as I was saying, in the case of hairpins, thickness which are not too large. So right now, with the power that are available, we are just addressing thin layers of copper. With increasing power, we can go towards higher thicknesses.
Okay, thank you again, Salvatore.
Thank you.
It's time to move to the next speaker. Next speaker is from Lumentum, Philip Leopold, laser processing of EV battery electrodes. Here you are, please. The stage is yours, 15 minutes, then maybe 1 or 2 questions.
Right, thanks. Thanks again for having us. I believe it's the first time actually you're having Lumentum, so thanks again for
It's
that.
a pleasure for us.
Good morning, everybody. So my name is Philip Leopold. I'm from Lumentum and basically in charge of our laser business in Europe. And today I'll go primarily upstream and focus primarily on the electrode. Why? Because it's the basic element of a battery. Without it, your car wouldn't be able, your EV car wouldn't be able to function. And 2, because it's actually the most expensive part you don't want to throw away when you go through your manufacturing process. So what I'll do is, if I can make this thing working, is after basically providing an overview of Lumentum, I'll basically go through why does the electrode processing with laser matters. Secondly, I'll go through what are we trying to achieve with this. And finally, why our PicoBlade 3 with FlexBurst, we believe, is actually a better solution as new technologies are being introduced on the market today. So first of all, let's start with Lumentum. Lumentum is a 1.7 billion organization, over 5,000 employees. You use our lasers every day, or the foundation of our technology is actually laser. So when you use the internet, you use our optical components that we ship to all a telecom equipment manufacturer. When you use your smartphone with a Face ID, you use our laser again with our VCSEL lasers. And obviously our micro lasers are deployed all over the world. So we have nano, femto, pico, and CW lasers as well. In terms of technology, we are vertically integrated. So we start at the wafer level and go up to the end product, the laser you would be using in your machine. And the optical content typically inside is usually Lumentum most of the time. And we make our own fiber, we make our own chips, and we assemble these in our facility in Asia, where we have 500,000 square feet. So this is our main facility in Thailand. And obviously we are using contract manufacturer located all over the world, typically in Taiwan, China, and Thailand again, to make sure we can address this fluctuating demand of our customers. So why does electrode processing matters? But basically, first of all, I think what you wanted to do is take it from the end user angle, first of all. You've all overheard that the battery capacity is going to go through the roof. It will increase from 500 gigawatt to 3 terawatts. Depending on the analyst, you can actually pick any number from 2 to 4, actually. So the demand is going to be big. We know that. However, what people know less is if you take, as an example, a BMW i4, 40% of the battery of the car is actually coming for the battery pack cost, and which represent the major cost item within the bill of material. 75% of this back cost actually come from the battery cells, the electrodes, and with the remaining 25% coming from the module and the pack only. So gigafactories as well, what you need to understand is they operate on a very low margin, a very low operating margin. And as you know that the cell cost has been decreasing dramatically over the last few years, and they expect it to decrease dramatically over the next few years by at least 50%, based on what we understand. It's actually very important for them to control the yield, the reject cost, and be able to support the highest throughput as possible. However, this trend started from Asia. I would say the Asian suppliers, in terms of gigafactories, in terms of ecosystem, in terms of machine builders, are literally 3 to 5 years ahead when you compare this to the machine builders or gigafactories in Europe or in North America. And they've been doing this for a long time. So for European and North American machine builders, the one who are slowly evolving, it represents actually a major interest sometimes to jump from the mechanical process to the laser process, because it's a risk, it's an investment going away from mechanical to laser, and it's usually the pain of doing the same is usually basically the less than the pain of change. So typically what you would see in Europe, for example, is in terms of machine builders, the big machine builders have already embraced laser, but the typical medium size, small size have not already embraced for this kind of technology. So before going through the laser itself, I wanted probably to share with you a bit more, for the ones who are not familiar with the electrode, what are they composed of, what are they doing. Basically, the cell comes in various form factors. They basically can be symmetric, prismatic, or pouch, or in blade. The cell are basically assembled then into module and pack, and the cell itself is composed of 4 parameters. The first one is the anode. The anode is a small layer of copper, typically in the tens of micron, with an active material on both sides, typically graphite. The cathode is aluminum-based. Again, it's a very thin layer in the middle of tens of microns or less, with an active material on the other side. There you have more exotic materials, and it depends a lot from a gigafactory to another. There's a lot of variability in that space, so that you don't have actually one size fits all. And you can have materials like NMC 622, 811, or any other type actually that they're looking at today. It's very versatile. The separator can be a sort of PET, PE, ceramic, or some other material, very thin. And finally, you have the liquid electrolyte in between, which facilitate the traffic of ions from one electrode to another. So the electrode, the anode and cathode, are manufactured of a very complex process, roll to roll. And there are so many steps in this process that actually, even if you consider a 1% reject rate, you end up with a 15% yield drop, which is huge, right, in terms of manufacturing. I don't know for you, but in our laser space, when we make lasers, having a yield impact of 15% is enormous, is not acceptable. In that space, it's the same. That's why they are dealing with a single-digit operating margin. And on top of that, new electrode technology are coming in, things like silicon anode or lithium metal anode, semi or solid state, oxide, ceramic electrolyte. My background is physics. I learned over the last 2 years more in chemistry than I wanted to imagine, to be honest with you. And there are many, many types which are going to come over the next 5 to 10 years to disrupt what people are currently using today, simply because they want your car to go longer and faster with this new technology. So the adoption curve that everybody saw so far is not going to be as exponential as everybody say. Yes, we're all going to drive an electric car at some point, but it's actually going to be slowed down because there's going to be raw material shortages. All analysts predict that nickel, for example, will be in short supply within 1 year. Lithium will be in short supply within 3 years, and cobalt will be the same. So there's going to be a bottleneck at the raw material level. Price is not going to go down as expected. It will actually be higher in 2022 in terms of material cost, in terms of cell cost. So it's going to make life tougher for the gigafactories and make sure they master even better their electrode manufacturing. So the window of opportunity for these machine builders is actually great, which means the one which we actually have not embraced yet, the laser technology, will be able to do so, and they'll be able to catch up the train. They haven't basically totally lost the battle here. So what's the technology used today? Today it's primarily mechanical solutions. People are using, for example, knife for cutting or using stamping. So you can see here in green on the right-hand side here, what people call slitting, which is basically when you cut the mother roll in two to get to the outer roll. The cutting is usually vertical, and the notching is when you create the tab. And the mechanical solutions typically are slow. They create damage. They create delamination. So if you see, for example, the common collector you see here on the right, you actually, with a mechanical solution, you do get occasionally a delamination between the common collector and the active material on both sides. So it creates actually safety hazards once assembled into module and packs. The module tools as well require maintenance. They wear and tear. A laser does the same. The laser doesn't wear and tear, but in terms of service time, a laser can run 20, 30,000 hours. A mechanical tool will not. You have to basically change it and upgrade it on a regular basis. So laser technology like nanosecond single mode lasers have been introduced over the last few years. Started first in Asia, but getting introduced slowly but surely in Europe and in the US. And they have improved as well the speed, and they have improved the quality. But this solution sometimes, and if you want to go into the details, require actually a cleaning process. So although the laser on one side is cheap, the additional step for cleaning is not so cheap when you consider the total cost of ownership. So what are we trying to achieve? So first of all, there are two conflicts. Actually, it's a three-dimensional problem. There are many conflicts in this problem. The first one is between cost and energy. If you look at actually how this electrode market is segmented, if you want to go low cost and low energy, there's many types of batteries you can find on the market today in Asia based on LFP type of electrodes. When you go into that of medium cost and mid-range of energy, NMC start to be the predominant technology of choice, 622, 811. And after there are more exotic materials when you want to go high energy. The problem of these, they become high cost, and it's not something you want to have in your car, and it's not something which will facilitate the adoption curve of EV battery. So ideally, you want to be low cost, high energy. On the other side, on the right-hand side, you see here, there's a second conflict between energy density and energy power, and power density, sorry. And usually here, the conflict is the electrode design is not the same. And you end up with two different types of electrodes. Usually the one which helps you to go far, but will charge slow, which the people call the marathon runner, which typically are thick and densified electrode with a thin collector. And on the other hand, when you want to have power, unfortunately, the one which charge fast and drive short will be thinner with porous material. This is very important because if you understand the chemistry and the structure of the electrode, you will understand that the interaction between the laser energy and the material will be different. So you can't use actually the laser in both configurations, right? So the interaction between the energy coming from the laser beam and the material will be different. Right, so now to make sure you understand even further, probably from a, I took this from a car OEM perspective, right? From a user perspective, all what this OEM car wants. They want to obviously extend the range. They want to extend power on one side. They want to improve safety. They don't want your car burned in your garage when you recharge it. And they want this to be affordable. They want the total cost of ownership to be low. So how electrode processing enable that? So first of all, to improve the range and performance, you need to improve the cell energy density and power. To do that, you have two options. You go below of the graph here, you improve the cutting quality. And to do that, what you do is you reduce HAZ. HAZ is what? Heat affected zone. Is basically equal to dead material. It's basically a loss of zone for energy within the electrode. Although it's so small, when you scale this to actually the size of the car and the number of electrodes you need, you realize you miss actually quite a good percentage which enable your car to go further. The second part, which is enable power now, it's more on the electrode structuring. What you do is, and you saw that in the previous slides, you create actually a pattern, small holes or other features within the electrode to increase the sort of wettability of the electrode, the contact surface area between the electrode and the electrolyte. And by doing that, you improve further the performance in terms of powering, in terms of cycling charge as well. Safety, the second factor as well for OEMs. And the gigafactories typically have to address that point by reducing particle contamination. To do that, again, it's cutting quality. And there you end up with two families of problems. One, which is the detached particles, the particle you don't want to end up on your electrode because they will short circuit at some point your electrode. They'll create basically runaways and make your battery to go in flame. And you want to make sure that the burr, which is the particle still attached. Okay, I'm saturating the micro. Thank you. Thank you very much. The second part is basically reducing the burr, which is sticking on the common collector in a Z and X axis. For the Z axis, it's the most important one. This is the one you want to reduce because it's going to go through, it's going to perforate the electrolyte and short circuit with the anode with the cathode. And typically what people are looking at is basically a feature which is half less than the size of the electrolyte. Oops, sorry. Go back. Finally, on the affordability side, you want, like I was explaining before, you make your cell more and more efficient. If you have more efficient cells, you need less and less cells, obviously. So you make actually your car going further, but at the same time, you make it cheaper. You want as well to improve the lifetime of the product. You don't want to change your batteries every 7 or 8 years like is it today. You want to improve that, and to do that, you go back to the electrode quality cutting by making sure you remove the quantity of particles or the size of the particles to do that. And finally, to improve this, the dilemma that gigafactories have, which is yield and being able to manufacture this in volume, it goes to speed. Now you need to improve the process speed, and it's about how many meters per second you can achieve with your laser. Obviously, the other processes like welding are important, but typically they are addressing the safety part. It's usually probably where laser manufacturers are focusing, because this is where the money is as well at the same time. But as well, the gigafactories need to look at where the tools they're using. And today, if you look at the tool they're using in these big gigafactories, the oven is predominantly the equipment which is taking the maximum size on the floor. And size is money. Size represents basically the number of probably of electrode they could manufacture more if they had more space available. So now let's make the connection between what I was describing to you before, which was taking it from the market, from the gigafactory perspective, from the car OEM's perspective, and basically relay this with our laser technology, or PicoBlade 3, and how FlexBurst can enable better quality cut. So our PicoBlade 3 is a high-power picosecond laser. It can go up to 200 watts in the IR, 100 watts in green, and 50 watts in the UV. It's got very high pulsed energy. It can go up to 8 megahertz repetition rate with a pulse duration of 10 picoseconds. Like every laser, you need a chiller and obviously a power supply to drive it. What's important here when you use that laser with electrode processing is actually the FlexBurst technology. You can use a thermal process like a nanosecond or single mode would use and cut like it was shown to you before. The problem is this one size fits all to cut an electrode is not totally right. If you start going into the details of the Haas in terms of contamination, the particle you are creating, it's very important you actually control that with probably a semi-cold process. The picosecond is by itself an ultra-fast, so it could be considered as a cold process, but you actually have to run it thermally and make it probably less efficient in terms of how it's going to interact with the material to make sure you can actually remove the right rate of material. So to do that, what we do is you create a train of burst within the pulse. So within the pulse, we basically create a profile of pulses, and the advantage of this laser is very analogous. It's not digital, so you can actually create a pattern, almost at will, to sort of preheat or prepare the material to make sure that you get the best removal rate at the minimum cost. And the minimum cost is obviously this impact, the drawbacks people were explaining to you before, which was Haas and particle creation, right? And what we can do is we can go up to obviously with different types of profile. We can play this at will. I mean, this is done in our application labs within Lumentum. Our engineers actually can help the machine builders. They can help actually the gigafactories to select which is the best profile to interact actually with their material, because each material again is different and will not behave the same way. And we validated that the Haas is reduced as you actually play with a number of bursts. The more bursts you have, actually less Haas you're going to have. And this has been validated as well by third parties in Asia who's been using this type of laser for some time. These are some examples we've been doing on anode notching, cathode cutting, or separator. Again, it's all about the quality. We're focused here about quality, not speed. So there's always a trade-off between the speed you want to achieve and the quality. The higher you want the quality, typically the speed is lower. And again, as you go faster in speed, the quality is lower. So in conclusion, the message to the machine builder is the pain of doing the same will be higher for you ultimately. You'll have to move at some point from this mechanical process to laser. Why? Because the material will change. I mean, the people, as I said before, want to go further. They want to go with better electrodes. And if you take, for example, the lithium anode, it's a very sticky material. There's no way a mechanical tool will be able to cut in the speed people were showing you before with a mechanical solution. So laser is by default the best option. To the gigafactories, today it's good enough. The cut quality, most of them are probably looking at from a visual inspection standpoint, or some of them are using microscope. But if they want to differentiate against the Asian suppliers who've been doing this for years, who have large capacity, basically you will see that quality is how they will be able to differentiate. And having the right laser to do that is very important to them. To the OEMs, obviously there are parameters they want to address. These parameters, I've explained to you to this before. They rely a lot how the electrode will be cut, and obviously they'll be able to influence. The one who have the technical expertise internally and to influence the technology are the key ones to, who should be talking to the laser manufacturer. What we've shown in our lab, and we're happy to share these results with you at our booth, but obviously not in public because this is confidential. We definitely show that PB3 enable electrode cutting in a better quality thanks to our flex burst. And finally, to the laser manufacturer, the world is, the future is bright for sure. And thanks again for your attention.
Thank you, Philip, for your very interesting presentation. Are there any questions from the audience? Yes, please, Johannes.
Thank you very much for your presentation. I enjoyed it a lot because in Munich I see a lot of parallels what we do at the Technical University in Munich in terms of conventional battery production, but also new technologies like all-solid-state technologies. And I have two questions, one concerning the product and one concerning the technology. So for the product, you mentioned new battery generations like all-solid-state batteries. Did you already try the picosecond laser, for example, for lithium metal or for ceramic electrolytes? And then from a laser perspective, you mentioned that you use megahertz pulse burst with a pulse spacing of, I think, 12.5 nanosecond. Do you plan to go to higher repetition rates within a burst and lower pulse distances, temporarily speaking?
I didn't get the second part. What's your second?
Like from the pulse burst, do you plan to go to gigahertz pulse bursts, or did you already try it also for electro cutting?
All right. So for the first one, we touched some new next generation electrode, which I can't share with you the details because everything we do is actually under NDA. So typically, what's happening is the gigafactories are sending us, or sometime the machine builders are sending us the material, the samples for testing, and we saw some next generation electrodes in our lab. At Lumentum, we haven't purchased. What we can do as well is purchase directly these sort of types of electrodes. So it's easier today to buy an LFP-based, an MC-based from an electrode service company and share the data publicly. So we've done that, but we haven't procured today, I would say, electrode from these sort of service houses, next generation electrode to do this kind of thing. So yes, we did. Unfortunately, we can't share the data. But if you have samples, I'm sure we can do this in our lab, or provide a demo at your facility to do the testing. So unfortunately, I can't give you a straight answer on that, but you understand the sensitivity of it, right? Because this is where the technology is, right? So the second part is, have we tried gigahertz? I think no. Our laser goes up to 8 megahertz. Is it something we could consider doing? Potentially. We have other new technology coming, new next generation laser coming in our lab. So we haven't done it yet. So not yet. I think, would we see the benefit? I think it depends. It's a trade-off between cost as well and the result you get, right? You need to, again, we try to benchmark ourselves against cheap lasers like nanosecond, single mode lasers, right? A picosecond high power is not cheap, all right? But again, it's about removing potentially the cleaning process or the cleaning parts that you need to put into your machine. So people shouldn't compare laser for laser. They should compare actually a laser plus what is required in terms of cleaning, right? Total cost of ownership. And there, the pico laser makes sense. If you start going in the gigahertz, the laser will be more expensive. So we haven't done it from a research standpoint. Does it make sense economically? We don't know, right? It's something we have to look at. But feel free to come to our facility in Zurich and to engage our expert here if you have any question on that topic.
Well, thank you, Philip. Are there other questions? Let me check if we have questions from the... No, nothing from the web. So I think it's time to have lunch. Thank you again.
Thank you.
And with this session, we have completed a session dedicated to the laser sources manufacturers. We have a new section this afternoon. So we have at least 1 hour and 20 minutes for lunch. So we restart at 2:10. Lunch is in the building outside this building. So also for people who are following us from internet, then we will start at 2:10. Thank you for the moment and see you later.